Next is work and heat. We have already defined the thermodynamic work. A system can be transferred from an initial stage to a final stage by means of a quasi-static process, and the work done during the process can be calculated as WIF equal to minus integral PdV. There are, however, other means of changing the state of a system that do not necessarily involve the performance of work, which means that without the performance of work, you can change a system from one condition to other. Consider four processes as shown in figure below, which involve closed systems. We have already described the terms like closed system, open system, etc. And a closed system means it is a system in which no matter passes between system and surroundings. So these are the four conditions, the four processes. All these are closed systems. That means this is an adiabatic wall. So if you are considering this as a system, there is no transfer of matter between this system and its surroundings. So this is your system and these are the surroundings. So four cases and we can explain them. So we consider the first two, A and B. In figure A, the system is a composite one consisting of water and a paddle wheel. You know what is a paddle wheel? So this is a wheel which can be rotated, and this is a weight or a mass which is placed here, and due to the weight of that mass, as you know, it will move downwards slowly. We are arranging it with some pulley arrangements. So when that mass is moving downwards, this paddle wheel will rotate. Paddle wheel means it is similar to that we are using in our uh, agriculture fields. You might have seen such pictures, or you can you have shown it. So when that paddle wheel is rotating, it can make some fluctuations in the liquid, which means that it can churn the water. It is continuously agitating, or it is continuously performing work on. So the paddle wheel is caused to rotate and churn the water by means of a falling weight. As a result, the temperature of water rises. And in figure B, the water and resistor continue the composite system. This constitutes the composite system. The electric current is maintained by the generator. The similar way, a weight is falling downwards, and when that weight is falling, this is a generator. So when that weight is falling, there will be a rotation, and due to that rotation, as you know, in a generator you have an electromagnet, or you will be calling it as the armature, or that armature is rotating in the magnetic field. So correspondingly, a current will be generated, and that current will be passing through this resistor. And it's a simple form that we are just describing. That is, by the falling weight, you are creating a current, and that current, when it is passing through the resistor, it is heating the water. Correspondingly, the temperature of water rises. This is known to us. When a current is flowing through a resistor, there will be heat generated by your Joule's law of electrical heating, I square RT. That equation is known to us. So, in both of these processes, work is performed by the falling weight and the state of the system is caused to change. That is why here we have written like this: due to work, the systems, this is the composite system, here this water and this falling weight, they constitute the composite system. And here water, this resistor, this falling weight, this generator, etc., they constitute the system. And this is the surroundings. And here in C and D, the situation is different. The system in both cases is water in a diathermic or conducting container. This you can see this is the case, and the system in both cases is water in diathermic container. In figure C, the system is in contact with the flame of a burner, and in figure D, it is in contact with the burning lamp. So, again, the system is caused to change its state without by means of mechanical energy. So, system is changing its state without by any means of mechanical energy. In the previous one, a weight was falling. So, as you know, when something is falling from a higher position to lower position, there will be a change in potential energy, or that potential energy is converted as mechanical energy, etc. All these are a form of mechanical energy. Potential energy is converted into kinetic energy. Kinetic energy and potential energy are two forms of mechanical energy. So here no such mechanical energy considerations. And you see that when a burner is here, there will be an increase in temperature of water. So this is a lamp, burning lamp. So when a lamp is placed, there will be an increase in temperature in the nearby area. So we have not mentioning the means by which the temperature of water is raising here. You are putting a flame here and you are putting a lamp here. That is only we are now measuring and now mentioned here. Okay, and we are not. So in the previous one it was work. So now our aim is to show that without the performance of work, you can change the system. Here we are changing the system means we are changing the temperature. So what happens when two systems at different temperatures are placed together is one of the most familiar experiences of mankind. It is well known that the final common temperature reached by both the system is intermediate between the initial temperature of the two systems. So one will be at the higher temperature, the other will be at the lower temperature. As you know, when they are putting in contact or when they are keeping in contact, they will reach an intermediate temperature. The changes occurring in figures C and D are the result of the transfer of something from the body at a higher temperature, because that lamp was at a higher temperature and the burner is at a higher temperature. So from that higher temperature body, something is flowing to the lower temperature body. And this transfer in the earlier days, we have assumed that something is flowing and that flow was known as caloric flow of heat. But now we are just mentioning it that it has the heat. So the transfer of something from the body at a higher temperature to one at the lower temperature, and this something we are calling as the heat. Therefore, we adopt the calorimetric definition. Calorie means, as you know, you are saying that light is traveling as photons. The similar way, you are saying that heat is flowing as something which is called as caloric. That is the term, calorimeter, calorie, etc. etc. That terms are known to us. So, according to that calorimetry, heat is that quantity which is transferred between the system and its surrounding by virtue of a temperature difference only. An adiabatic wall which does not allow the flow of heat is called, therefore, a heat insulator, and diathermic wall which transmits heat is called a heat conductor. The decision to whether a process involves the performance of work or the transfer of heat depends upon the choice of the system and its surroundings. This is an important one. So, whether work is done or whether there is a transfer of heat, all these terms, all these things depends on the choice of the system and its surroundings. As an example, in case B, and this was our case B, this one. Just look that figure. If the resistor is regarded as the system and the water as its surroundings, then there is a transfer of heat from the hotter resistor by virtue of the temperature difference between the resistor and the water. If a small part of water is regarded as the system, with the rest of the water being considered as the surroundings, then again there is a transfer of heat. The surroundings of the composite system, comprising both the water and the resistor, do not contain any object whose temperature differs from that of the composite system. So, no heat is transferred between this composite system and its surrounding. In this case, the thermodynamic state of the composite system is changed by the performance of work by mechanical means, that is, the falling mass. You can see this. So, if you consider this as the system, so this is something surrounding. So, this resistor, when it is heat is when current is flowing through it, it is causing heat. So here the temperature of water is increased by the transfer of heat from this resistor to water. So in other words, you are considering this lower portion and upper portion. Then the lower portion is heated by the transfer of heat from this upper portion. So, if you consider this as a composite system, so inside that system heat is generated. So, we are not at all bothering about the transfer of heat from surroundings to system. In that case, you can see that this weight is falling. Weight is falling means that it is performing some work. So then this work is converted as, or this work is changing the state of the system. That means temperature of the system has raised. It is due to the performance of work by the system. But if you consider this water and resistor, it is the heat from that resistor is increasing the temperature of water. So, from this discussion, it is clear that according to our choice, that means this one, the decision of whether a process involves the performance of work or the transfer of heat depends upon the choice of the system and its surroundings. So, we have considered the cases. Next, a term, adiabatic work. We have already described the term work. So, the system we have just mentioned what. Consider a closed system which is completely surrounded by adiabatic boundary, like this. There is a slight difference between this case and the previous one. So, here your liquid and only resistor are here and the generator and falling weight are outside. So the system is coupled to the surrounding so that work may be done. The work done under adiabatic condition is called adiabatic. So under adiabatic conditions, the condition is that you can perform work on the system, but no heat transfer is possible. The performance of work for the system means that if you are moving one of the sides, that means you can apply pressure on it. Or if system is applying pressure, that means this can move outwards. That means work is done by the system, and if this is moving to this side, work is done on the system. So the work done under adiabatic conditions is called adiabatic work. So consider the composite electrical system composed of resistor immersed in water as shown in figure. The initial state is characterized by PI/TI, pressure and temperature, and the final state by PF/TF. So we have an initial condition, a particular pressure, particular temperature. You are changing that particular initial condition to a particular final state given by PF and TF. The state of the system is changed from I to F along the path the first. That means by the performance of adiabatic work only. To perform adiabatic work, the water is surrounded by adiabatic walls. The pressure is kept constant. The mass is allowed to fall down. That means here next just we have mentioned that the change of a system may be either performance of work or by performance or by the transfer of heat. So here the system is moving. That means a work is done, and that your system is thermally isolated. So the work that you are doing corresponding with respect to that system is an adiabatic work. And by the performance of this work, that means this weight is moving from this, say, at this higher point to a lower point. So that work is performed, that weight is performing work. And due to that work, that energy, mechanical energy, is converted as electrical energy. So the pressure is kept constant at Pi. The mass is allowed to fall down, which turns the generator. The current produced by the generator heats the resistor, and the temperature of the water is raised to the required value Tf. So corresponding to that value Tf, you will have a pressure Pf. So by this way, that means one way of performing adiabatic work that we have shown. But this was our first part. You have kept the pressure at a constant value and you have changed the temperature. And we are assuming that the pressure remains constant and not as Pf. Just your initial value is Pi, temperature Ti, final pressure Pi and temperature Tf. This is the track. And this is not a pressure volume diagram. It is a pressure temperature diagram. And here you can see that there are paths second and third like this. You can move through IABF or IDCF. IABF is path second and IDCF is path third. If we choose path second, we might first compress the water adiabatically from I to A. You can see that there is an increase in pressure. And how can you do that? By the performance of, say, you can move this wall to inside. So pressure is increased. So now what happens to temperature? You can see that temperature has also increased. Then at this point A, we can use the current in the resistor. That means in that time pressure is keeping constant and by the passage of current through the resistor, temperature has increased to a particular value at B. And you can see that that may be greater than this your TF. And then we will expand. We have an initial pressure Pi. You are changing it to some other value. Again, you are reaching that same pressure Pi. So, for that you have to move the piston or you have to move the wall to outside. So, that is this case. IA is adiabatic compression, and this A to B, you are passing the current through a resistor, and from this B to F you have adiabatic expansion. And similar here you can first see in the path third an adiabatic expansion, that means pressure is decreasing. Then by keeping current, that means pressure constant, you are increasing the temperature to a particular value, and then you are again compressing. So first you have expanded, that means from an initial point of the wall, you can slightly move to outwards, then pass the current, then again to the initial point. And it is found that these three are the not possible ways. There are infinite number of paths possible by which a system may be transferred from an initial state to the final state by the performance of adiabatic work only. The experiments show that the adiabatic work is the same along all such paths. The generalization of this result is known as the first law of thermodynamics. So, how can you calculate the adiabatic work done here? The first one, the system is falling from here to here. Say example, so it is like slowly moving. So current is passing. So for a particular time, current is passing, and at that time, that means when temperature has changing from Ti to Tf, you can measure during that time the movement of that weight. If you know the mass, you can find the weight, or if you know the mass, you can find what is the change in potentiality, etc. And that change in potential, that means your equation mgh, the distance through which the mass has fallen. And from that equation, that potentiality has changed to, or that change in potentiality is the work done that is performing in this liquid, that you can directly calculate. The second way, you are just moving this to outside, so you can find the change in volume as well as pressure, it is PdV, and the compression, etc. First you have compressing, then expanding, you can find the work done, and also in that case also you have the falling of weight, there also you can find the energy change. So by adding that three terms separately, you can find the total work done. That is possible. And it is found that in all such cases, the adiabatic work done is different. And actually this is a contrast. In the diathermic work, or we have in the last class, we have mentioned that work depends on the path. That is why you have written it as d bar w. Work as d bar w. Work depends on path. But if that work done is adiabatic work, it is independent of. If it is adiabatic work, it is independent of path forward. So the experiments show that the adiabatic work is the same along all such paths. The generalization of this result is known as the first law of thermodynamics. And you can set make the statement as, if a closed system is caused to change from an initial state to final state by adiabatic means only, then the work done on the system is the same for all adiabatic paths connecting the two states. The example, I and F are the states. So, if a closed system is caused to change from an initial state to a final state by adiabatic means only, then the work done on the system is the same for all adiabatic paths connecting the two states. Whenever a quantity is found to depend only on the initial and final states and not on the path connecting them, an important conclusion can be drawn. You can call such a function as a point function if it is not depending on path, and if it is depending on path, it is called as a path function. So adiabatic work done is not a path function. In mechanics, the work done in moving a body from one point in a gravitational field to other point in the absence of friction depends only on the positions of the 2 points and not on the path through which the body was moved. It was concluded from this that for a conservative force, that term we have already, it is already known to you. A conservative force field means, actually conservative force, you are saying that if you are working in moving a body around a closed path, you are calling it as 0. So, if you consider 2 points, from one point to other, you have a work done, and from the second one or initial point to final point, you have work done. Then from final point to initial work done, the work done is same, but you are moving in the opposite direction, so it is negative. So total work done you are taking as 0. Then that is a definition of your conservative force field. So in such cases, there is a function of the space coordinates of the body whose final value minus its initial value is equal to the work done. And this function you are calling as the gravitational potential energy. And the similar case you have in electrostatics, the work done in moving a positive charge from one point to other point is independent of the path followed. So you are saying that work done is equal to the difference between the electrical potential energy between the 2 points. So this adiabatic work is somewhat similar to that. In moving from one point to other point, the work done is independent of the path followed. So there must be some thermodynamic coordinates whose value at the final state minus initial state is equal to the adiabatic work. And according to the first law of thermodynamics, therefore, there exists a function of the coordinates of the thermodynamic system whose value at the final state minus its value at the initial state equal to the adiabatic work done in going from one stage to the other. This function is known as the internal energy function. Like your gravitational potential energy, electrostatic potential energy, you are calling this as the internal energy function. And denoting the internal energy function by U, we have Wi to F adiabatic. That means work done in going from I to F adiabatically equal to the final state, initial state to final state work done equal to change in internal energy of final state minus initial state, where the signs are such that if positive work is done on the system, its energy increases. That means if work done is positive, UF minus UA is positive, which means that UF is greater than UA. That means internal energy increased. And that's all in this class. Thank you.